that has been said yesterday, but just in case, I will recall the most important parts of the picture so that we can then move into seeing a couple of the details of the proof. So remember that we have an Artin group, which is defined with representation of this type, and we focus on Artin groups that arise from reflection groups in Rn. So either from a finite Coxeter group or from an affine Coxeter group, and we call these classes spherical and affine. Okay. So basically, I will give some examples based on spherical cases. And remember, the focus of our theorem, let's say, is the affine. And we have this generalized configuration space, which we denote by YW, which can be defined for any Coxeter group W, but it is easier to do it if W is a reflection group. And in this case, we have this expression here for this configuration space. The most fundamental example being the case of braid groups, where this is the case. W is the symmetric group on 3 letters, and the corresponding Artin group is the braid group, which is the fundamental group of the configuration space. Okay, and one more bit of information on top of yesterday is that the CW complex that Mario has introduced at some point. So he didn't tell you, but that CW complex is everyone calls it the Salvetti complex. So it exists. It is defined for any Coxeter group W, and it is a CW complex with the same homotopy type as the configuration space YW that we want to study, and its cells are indexed by finite parabolic subgroups of W, standard parabolic subgroups of W. And this is the example for the braid group on 3 strands. Okay, and the Salvetti complex looks like a hexagon with some identifications of the edges. Okay, and as you know from yesterday, the K-1 conjecture says that YW should be a classifying space for the corresponding Artin group GW, which means, for example, equivalently, the universal cover should be contractible conjecturally. We have seen that the spherical case was done 50 years ago by Pierre Delisle, and there has been, so here I'm skipping some intermediate cases that were then generalized afterwards. So that's why the story is a bit compact here. There has been some research in the direction of using metrics of non-positive curvature to prove that the universal cover of YW is constructible. But I will not go into that part of the story. This is the second line here. I will focus on the third line, which is the affine case that we've been working on. Any questions so far? And still, reminding from yesterday, one way to reinterpret the proof by Delisle is with the language of Garside groups and Garside structures, for which we have this nice construction, which Mario told you. So you can start with any group, for example, a Coxeter group, and a generating set you take the interval in the Cayley graph. Okay, we have an example over here, again for the symmetric group on 3 letters. You can construct the interval group, which is the group with the generators that you see as labels of the edges in the Cayley graph, and subject to the relations that you see again in this Cayley graph. So, for example, here there is only one relation. There are 2 generators, A and B, and there is one relation ADA equals BAB, which comes from setting equal 2 different paths from one point to another point in the Cayley graph. Okay. And so, okay, this is just a construction. And the point of this construction is that if this interval is a balanced lattice, then the interval group is a Garside group, and we are very happy when we have a Garside group because it carries very strong properties, algorithmic and topological properties. In particular, the main reason why we like it for the purpose of the K-1 conjecture is that there is this very explicit construction of a classifying space of a Garside group, which basically, so I mean, Mario told you already, so just a different angle to look at this. You can take the order complex of the interval on the left and quotient it, identify faces based on the labeling, essentially, so that the simplices are indexed by partial factorizations of elements in Inven. Okay. The main motivation actually for Garside groups is that they arise if you want to study spherical Artin groups. In fact, the spherical Artin groups have 2 generally distinct Garside structures. On the left, we have the standard Garside structure, which is the one that you get if you use the simple reflections as generators. So you take a finite Coxeter group, you take a set of simple reflection S, okay, and you construct the Cayley graph. You take the interval group. This is the corresponding spherical particle. However, there is this more recent dual presentation of spherical Artin groups, which gives rise to a very different, combinatorially different way to look at spherical Artin groups, where basically we have one generator for each reflection now of the Coxeter group, and we can read the relations by fixing a Coxeter element over here and looking at this interval, which is known as a non-crossing partition lattice. Okay. So far, so good. I'm being a little bit quick, but in my defense, everything was said yesterday. So maybe you should complain that I'm losing time here. So yeah. This example was not shown yesterday, I think. So I told you that there is this general construction of a classifying space for a Garside group. I told you that spherical Artin groups have 2 Garside structures. If we use the dual one, which is the one we will be using the most today, this is what this classifying space looks like. So it's 3 triangles with identifications of the edges.
In which sense it's dual?
Now that's a great question. It is dual because there are several, let's say, numerical properties that get exchanged when you pass between standard and dual. For instance, the number of generators on the left is equal to the height of the poset on the right, and vice versa. So on the left we have 2 generators, and the Gaussian element has length 3. On the right we have 3 generators, the Gaussian element has length 2. And this is true in general, and there are other kind of numerical invariants, if you want, that get exchanged between these 2 structures. That said, there is no well-established theory of duality in finite Coxeter groups that fully explains, what's actually going on. So partially, the answer is that we don't exactly know. But yeah, that's a very, very reasonable question. Okay, so this is the, the classified space that you would get for the break group on these strands using this dual structure. That's good. So now I gave you a couple of examples. Actually, a worked out example for the spherical case, but we want to dive into the affine case now. So the main running example is going to be this one, which is the case A2 tilde, also known as affine braid group. So what happens is that we want to fix a Coxeter element because this is how we build this dual structure. We have all reflections as generators, and we fix a Coxeter element, which is any product of 3 simple reflections. So, for example, we fix this chamber as our fundamental chamber, and the product A times B times C is going to be our Coxeter element, which will kind of characterize this dual structure and the dual presentation that we are going to end up with. Okay, but first thing, we would like to understand this interval a little bit better. So we are for now inside the Coxeter group, where things are somehow more understandable than in Artin groups. We are in this Coxeter group, and we want to understand the interval between the identity and the Coxeter element using all reflections as generating set. Okay. So basically, we need to understand what are all minimal length factorizations of a Coxeter element as a product of generators of reflections. So a Coxeter element ABC, if you do the explicit, you see it explicitly, it is a glide reflection across this axis. So basically, it reflects and translates upwards. This is what it does. And it turns out that to build minimal length factorizations of this Coxeter element, you can start with any reflection that crosses the axis. So there are like infinitely many of them, all this. Or you can start with B or B prime, okay? But you cannot use the other reflections that do not cross the axis. Okay, this is kind of an elementary observation which holds actually in all affine cases. So this motivates giving a name to these 2 different types of reflections that we have. The ones that cross the axis, we call them vertical, and the ones that do not cross, we call them horizontal. Bear with me. So why should the vertical ones be called horizontal? The reason is that the orthogonal vectors, which are roots in the root system, so the ones orthogonal to the hyperplane that do not cross the axis are horizontal. So horizontal refers to these two vectors being horizontal. Let me check how I'm doing on time. Okay. Okay. So these reflections, will form the level 1 of our interval, and then we should also figure out what's on level 2, and then on level 3 we are going to have just the Coxeter element W. So this is like a length 3 poset with one minimum, one maximum, and infinitely many elements at level 1. And also the level 2 is actually quite easy to figure out. Turns out that you have one rotation for each of the colored vertices and 2 translations. Okay. So there are kind of 2 translation directions which work out and nothing else. Okay, so this is how the interval looks like, and I gave you this in a explicit example, but most of the overall structure actually carries out the general case. So there are going to be, for example, at level 1, we're going to have infinitely many reflections, all those that cross the axis, plus a finite number of reflections that do not cross the axis. Okay, and this distinction between vertical and horizontal was actually developed by McCammon already when he proved that actually he characterized when this interval is a lattice. And as Mario told you yesterday, this is not always the case. And in fact, the interval between the identity and the Coxeter element is a lattice, if and only if the horizontal roots form an irreducible root system. And this happens in the case C tilde, in the case G2 tilde, and in the case A and tilde, if you choose the right Coxeter element, so not for Coxeter element. But the bottom line here is that in most cases the interval is not a lattice, which means that it does not give rise to a Garside structure, which is kind of sad since we were hoping to use the whole Garside groups machinery to study affine Artin groups. And there is an explicit characterization of when the interval is a lattice and when it is not. In fact, McCammon and Salvetti also gave a construction of a kind of completion to a Garside group, where basically they extended the Coxeter group W with some extra translations. And these translations are built so that the interval in this extended group becomes a lattice, and basically our Artin group, affine Artin group, is going to be embedded into a Garside group that comes from this interval. So this was more or less the context where we started working on this problem. And this is the outline of the proof that we developed. Again, these 3 steps are the same three steps that Mario told you about yesterday. So I'm still kind of in the preliminary part of the talk. The first point is the more topological part, and it is also it's comparatively short with respect to the whole proof, but it may be regarded as maybe the most surprising one, because basically it says, okay, forget that we don't have a Garside structure, build the interval complex exactly as in the Garside case, and we show that that interval complex is a classified space anyways, even though the standard proof for Garside groups does not apply because we don't have the lattice property. Okay, so this is point one. This is now already a significant step forward, because before, if you just use this construction, as we saw yesterday, already gives you a finite dimensional classified space for affine Artin groups, because you can, they embed into a Garside group CW. So there is some covering of the classified space of CW, which is finite dimensional, and it is a classified space for our group. The problem is that this covering is very, very large, and by very, very large, I mean very, very large. That it is indexed by cosets, and these cosets are not really something that we can very explicitly work with. So effectively, it's still too large to. It was too large for us to do anything practical. So instead, this KW, now this is indexed by objects in the Coxeter group. So I can tell you the synthesis of this complex. It's something even my computer understands the synthesis of this complex. Okay. So once we got this, the idea was, okay, now we need to prove that it is homotopy equivalent to our configuration space YW. So the second step that we went through was to find inside KW a subcomplex which is homotopy equivalent to YW. Okay. And by the way, it is also finite subcomplex. And we did this for, so this is the only step which easily works out for any Coxeter group W, whereas the other steps, it's unclear whether they will generalize or not. Very well. And the third step, which is the longest one, was to construct a deformation retraction from KW to this subcomplex XW part. So yeah, I've come maybe 20 minutes into my talk, but I'm maybe even more. But I'm still kind of, I've just now arrived catched up with what Mario said yesterday. So in a sense, you didn't miss anything. So I guess that. Long lunch. Yes.
No, we were sorry.
No worries. So this proof, for which I will give you a couple of details soon, first it implies the Capable conjecture because, because it does, but also it implies that this dual presentation that we used, it gives the same group as the standard affine Artin group, because KW, the fundamental group of KW is this dual Artin group, whereas the fundamental group of XW prime is the standard Artin group. So the deformation reduction also tells you the isomorphism of these two groups, which is good. Okay, are there any questions? Okay, so depending on how I will do on time, I will try to give you some details of all the 3 points here, which are fairly independent. They are completely independent on each other, save for the fact that you need to know what x prime is in the first step, and x prime is defined in the second step. But you know, that's basically they are independent steps. So step 1, as I said, it's the topological step, proving that KW is a classified space. So we started from what McCammon and Salvetti gave to us, which is you know, an affine Coxeter group, which is generated by horizontal and vertical reflections, as I defined earlier. They extend it to, they call it a crystallographic you know, group, which is not a reflection group anymore. And they do it by adding certain new translations. Okay, it's, you know, we will not go into the details of how these are defined. And they also give us, you know, they also introduce these other groups, which turn out to be quite useful. Again, not going into the detail, I will give an example soon. So, okay, just you know, believe that these groups are useful. And on top of these groups, so the black groups live in the Coxeter world, and then we have the Artin world, which is the red one, where we have our affine Artin group here. So this is the dual affine Artin groups, if you still don't want to believe that it is isomorphic to the standard one, which will be a consequence. Okay. Here we have this Garside group that McCammon and Salvetti constructed, and turns out to be useful to have also the Artin analogs of these 2 bottom groups, of which the left one is also Garside. So basically we have this diagram where on the top left there's the group we are interested in, and on the right we have 2 Garside groups. Okay, and now we take the same diagram and we look at all the interval complexes that are naturally associated with these 5 groups. So KW is the one we care about. KC and KF, these are classified spaces for the corresponding Garside groups. And then we have KD and KH, which we will go into in a moment. And now basically, so why did I introduce this diagram, which you know, it's unclear why it would be useful. The point is that now we go around this diagram to carry around the classified space property, more or less. In fact, based on properties of inclusions between these complexes, it turns out that if 3 of these are classified spaces, then also the 4th one has to be. Okay. Not difficult at all to see once you know the complexes. So that's good. So basically, you know, it is enough to show that this KD is classified space because we know it already for KF and KC. And the same holds here. So up to homotopy equivalence, there is these 2 complexes are related by a covering map. So one is classified space, internally the other is.
So my Vittorius is homological.
Sorry.
My Vittorius is homological.
Yes.
But you're doing the homotopy.
Yes. Yeah, no, that's true. So each of these is a classifying space, if and only if the universal cover is constructible, if and only if the homology is trivial. Yes, this is. So it's not particularly advanced. Yeah. So that's it. Yeah. So basically, a lot of the interesting information lies in these two complexes here. And in fact, this complex KH basically it indexes the partial factorizations of our Coxeter element, which only use horizontal reflections, essentially. And horizontal reflections, the horizontal root system is, in general, it decomposes as a union of possibly a couple of orthogonal root systems. So this KH decomposes into a product of a couple of complexes, each of them indexing, only the parts of the factorizations which use certain directions of the horizontal root system. And I try to make an example here. So an example which can explain to you what KH and KD look like. Let's see. So it's a four-dimensional example. So it's not, I will test a little bit of your four-dimensional way of thinking. But it is almost like one of the smallest examples where the poset is not like this. So I couldn't do much better than this. So the example is the case D for tilde. This is the Coxeter diagram. If you like to think in terms of Coxeter diagrams. Or simply speaking, we are in R4 and we have the four reflections with respect to the four standard hyperplanes plus this reflection that intersects all of them with pi/3 angle. And if you take the product ABCD, this is going to be glide reflection or higher dimensional generalization of a glide reflection with an axis which is orthogonal to this hyperplane. And it turns out that the directions which are, direction of hyperplanes that do not cross the line orthogonal to this hyperplane, so are basically, correspond to roots in three orthogonal directions. So there are basically three irreducible components of the horizontal root system, and those are spanned, by these three roots over here. So if I go back quickly to this picture, so here we have the case A to tilde, and the interesting stuff was happening inside this strip here, which was delimited by two horizontal hyperplanes. Okay, very well. And in the D for tilde case, we have the same, but the strip now is a cube times R, so which is something in dimension 4. So we have, instead of just two walls for the strip, we have three pairs of walls which are orthogonal to each other, times R, which is the axis of our Coxeter element. And so it turns out that basically the complex KH, which tells you the horizontal parts of factorization of Coxeter element, factors as a product of three simpler complexes, which are just a wedge of two circles. And these two circles correspond to the two opposite reflections in this cube, basically. Because you can use, for example, R1. If you use R1 in a factorization, you cannot also use R1 prime, which is the other one. Anyways, so basically, this is what the complex KH looks like, and the complex KD is just KH times an interval where we identify top and bottom of KH by swapping the two reflections in each of these subspaces. Okay. So this is, just to. So this example, either you actually follow it, which is plausible, or at least it's to tell you that given an explicit example, KH and KD are actually small enough and easy enough to construct that we can understand. And in fact, this complex here, this is a classifying space because it's a product of the classifying space. So, for example, this is actually a proof that KW is a classifying space in the case before tilde, because we went all the way down to KH. So KH is a classifying space. Yes.
Okay, go to the next slide. You said something there is a product. Not this. Oh, KH is a product, but not KD. KD is some kind of mapping focus, right?
Yes, yes, exactly.
So it's not a product.
KD is not a product, yes. But KH is, which is the important thing. And in general, in fact, we use the fact that KH is a product in the following way. So if KH is just a single component, then it means that the interval was a lattice. We were in one of the lucky cases where we start with a lattice. And so KW is a classifying space, so KD is a classifying space, so KH is a classifying space. So if KH is not, is irreducible, then it has to be a classifying space. Oh, I did something. Okay.
Can I just kind of press on that point?
Yes.
The last line. So KW is also is. I mean, you need something about the fact that the identification is done over a sub K by 1, sub-spherical space. If you just do some kind of and the gluing is not done like around the K by 1, you don't get the K by 1.
So we are using basically like both this diagram and the diagrams on the fundamental groups. They are both push outs, for example.
So it's injectivity of those maps.
Yeah, exactly. So
and the fact that the subcomplex is the K by 1.
So if you write the Mayer-Vitoris exact sequence for the homology of the universal cover of KC, you will have basically you will see the homology of these four complexes in this exact sequence. So if 3 of them vanish, then the fourth one vanishes.
I understand. I'm not talking. Maybe go back to the example. The example, the gluing was done around a wedge of circles, right?
So
no, around the whole copy of KH.
Yes.
Oh, I misunderstood. You just swap those, but
yes.
Okay. You don't need what extra information. Okay.
Okay. Other questions? Okay, so KH, if it is alone, it is a classified space. Okay, but if it is not alone, it is a product of smaller complexes which can appear alone. So, and this is maybe slightly tricky step, but this basically implies that if KH is a product, all the single components are classified space because of what I said before. So the product is also classified space. So KH is a classified space, so KD is a classified space, so KW is a classified space. I will give you 10 seconds to digest this because you want to ask a question.
So how do you get from KD to KW being a classified space?
KD to KW is the Marionett's subtract sequence on this for.
Forget about my idea first.
Okay.
Just KD is K by 1, right? And then what else? KF is K.
Yeah. Also,
Okay,
yeah. So KC and KF they are K by 1s because they come from gas side groups. Yes.
Oh, that's we pull a rabbit.
No, I think I said it before, but maybe I was quick. Yes. It's the green tick is being a classified space. So we know it for these two, and these two, one is if and only if the other is. So yeah.
And you know that all the maps are injection.
Yes. Also yes. Yes, I'm not saying everything. Okay. So this was step 1, and for step 2, inside this KW, we wanted to find a copy of our orbit configuration space YW, and the way we do it is we take the standard Salvetti complex. Which is a union of cells, each of them looking like a Salvetti complex on its own. So what we do is we keep the global combinatorial structure of the Salvetti complex, but we replace each cell or each subcomplex with each dual counterpart. It's KWT. This is the interval complex associated with the spherical subgroup WT. So, and these are classifying spaces because the spherical case is well understood. So basically, we took the standard Salvetti complex. And we replaced all the cells with kind of the dual their dual counterpart, which almost by definition gives us not equivalent complex, which sits inside our KW. And this is the example ATT. So you may remember from yesterday that the standard Salvetti complex in this case looked like 3 hexagons with some identifications. Here, instead of the 3 hexagons, we have 3 subcomplexes, blue, green, and red, which correspond to these 3 points here, and they intersect a little bit. So the blue and the green, they intersect in the complex coming from this reflection A1, for example, and same for the others. In the same way as the cells of the standard Salvetti complex intersect. Okay, and this is a finite subcomplex. As opposed to KW, which is okay. And we come to step 3. So step 3 is the longest one. So I will give even less details here. The starting idea was to arrange the cells of KW into components. For example, in the case, this is the case A to tilde. There are 9 components, 7 of which are infinite and 2 of which are finite. So these are all all simplices of KW, and these components are designed in such a way that all these small Hasse diagrams look bipartite, and the black dots, like the full dots, correspond to the simplices in our subcomplex XW prime. So we kind of have a pictorial way to write down all the simplices, and in particular the ones that we want to get at the end, which is XW prime. And using discrete Morse theory, it is fairly easy to show that for each of these infinite components, you can actually collapse from infinity to the right and to the left, so that you only end up with this finite sum portion. So this picture here also contains this intermediate step where we actually end up with a finite part of KW, all the simplices shown here, of which like we need to collapse a bit further because we want just the black dot essentially. And for this second stage of collapsing, it turns out that to construct this collapsing sequence or discrete Morse vector field, however you want to think about it, turns out that the language of lexicographic shellability is particularly useful, like it seemed to really fit the situation. So as an intermediate step, we constructed an ordering of the reflections that make our interval lexicographically shellable also. Which means in this particular instance that every element of our interval has a unique factorization which is increasing in the sense of the ordering that we are introducing. And this increasing factorization is the lexicographically smallest one and also the co-lexicographically largest, which means that if you can build it in a greedy way by picking the smallest reflection that you can use, and then the smaller reflection that you can use for whatever remains, and so on. So why is this construction useful? Without much detail, the point is that we define our discrete Morse vector field by matching cells using these kind of canonical factorizations that we got. So, for example, the one simplex indexed by the considered element itself, we split it into A1 pipe PC0 because A1 is the smallest reflection that divides W. So we kind of get canonical directions to proceed in our collapsing. And so I told you more or less how we use it. Now I will tell you more or less how we construct this ordering. And the idea is to start from our fundamental chamber and travel in the positive direction of the axis. And we keep track of all the reflections that we need going up. And then at the end of this, when we arrive at infinity, we put there the horizontal reflections, in this case B and B prime. And then we go back to minus infinity and travel up until the base chamber. And we see all the remaining vertical reflections. So this is like a way to order the reflections in the interval, and turns out that this makes this ordering of the labels of the poset makes it execute Affiliation. And it does not come completely out of the blue. In fact, the more or less classical way to shell finite non-crossing partition lattices can be interpreted in a similar way. For example, this is the symmetric group on 4 letters. And it turns out that you can see it as an arrangement of lines on a sphere, and there is still an axis as we have in the affine case, and the order of like one good order of reflections comes from traveling along this axis, in the positive direction, basically. Are there any questions? Very well. So, what happens now? What I described to you with a little bit of details, but not too much, is a procedure, a 3-step procedure that we employed to prove the Capable conjecture. And most of our proof is very specific to the affine case. Everything except step 2, which was building this dual version of the Salvetti complex. That's done in full generality. But that said, we actually don't know if the other steps are generalizable to other cases. So there is no clear obstruction that makes them unappliable. Okay, this is what I'm trying to say. So in particular, we don't know if maybe KW is a classified space more generally. It's interesting to ask if these intervals are shellable, and well, also the isomorphism between standard and dual Artin groups, that it fits the picture, and it's a natural question to ask. We were also asked other questions, like can we do affine complex reflection arrangements? Can we do affine superficial arrangements? This is still Pierre Delin who was asking questions, not just doing remarks. And he cares about superficial arrangements, which makes sense. And we don't know here very well. As for the last slide, what we are actually doing, and it is working, is the rank 3 case in general. So with 3 generators, so in some sense quite basic. 3 generators, but beyond affine cases. So most of the 3 generators case is of type hyperbolic. So like the Coxeter group generated by reflections with respect to this arrangement of lines in the hyperbolic plane. And in this setting, basically we carry over all the steps of our proof of the Capable conjecture in the affine case. So the interval is a lattice. Again, this plays a role in the rest of the proof. The paper one property, which was known before in this case. So the paper one conjecture is not new in this case. But shellability and the isomorphism between standard and dual, I think they are new. And also a solution for the word problem. That's also, yeah, that's supposed to be new. Because so this case is Gauss-side. So the dual Artin group in rank 3 has a Gauss-side structure. The point is that we prove that it is isomorphic to the standard one. So, and then we can use the dual Gauss-side structure for the standard one. That's it.